Hi, so welcome to this video about the presentation of the lecture number 11 for compiler design. So we're going to be seeing, well, first some updates. So this is the lecture that we are covering right now. So the slides, I have made extensive changes to the slides. I believe it's much better now, much more complete, especially regarding how to do the stack frame allocation for the execution of the functions. So I included a complete example about that. It used to be explained, but not with a complete example. So if you had downloaded the slides before, you have to go back and update the slides. So for those of you who have not seen, for the assignment number 3, for the schedule, if you go to the schedule here, and you can actually put your name on the schedule. So please do that as soon as possible. The demonstrations are on April 2 and 3. So that's about it for the updates. So if we can go to the matter of the subject for today. So this is the continuation of the lecture for code generation. So we're going to be talking more details here, how to allocate memory using the Moon assembly language, also all kinds of memory access for the atomic variables, the integer in particular. Many of the examples I will show will be using integer variables. I will explain how to do the access of arrays or objects, but many of the examples will be actually using integer variables. I will show how to access the other kinds of variables, but then you have to combine them with particularity if you're using aggregate data types such as objects and arrays, then you have to use offsets. So when I show the examples, I'm rather showing using integers so as to not complicate the examples by having to add another layer of offsetting into the explanations of the examples. And we're going to go and talk about how to do the code generation for expressions, and then the assignments. And then eventually we'll go to how to do the function calls. I'm going to show how to do function calls using tags-based approach, as well as a stack-based approach. In general, the tags-based approach is more easy, but once you understand how to do the offsetting, the offset-based approach and the stack-based approach is not so complicated after all. So here we go. So how do you do variable declaration? Let me fire my pointer here. So how do you do variable declarations, or how do you, what Moon code corresponds to your variable declaration? So in this slide set, I've updated the coloring somehow. Whatever you see in green is the source code you are compiling, and whatever you see in blue like this is the actual Moon code. I've actually put in light blue the tags that you may have in your Moon code. So whatever you see light blue identifier means it's basically referring to a tag in the code. So if you have an integer, well, one of the assumptions here I'm making is that an integer is actually 8 bytes. So which is the length of a word into in the Moon assembly code. So if you see a variable declaration for an integer, that means you actually must reserve a word that will store this value, in which case actually you use the reserve, memory reservation, RES instruction to reserve 4 bytes. So that's basically here. When you have this variable x, you generate a label for this variable. That is, again, if you're using the label-driven approach. Then if you have variable x, then you actually, which is an integer, then you actually reserve 4 bytes for this variable x, and that's the code you are generating for this particular variable. In this case, x is an alias. That is an alias in your Moon assembly code that actually corresponds to your variable x. Note, as I said in the previous lecture also, that if you have more than one variable x in 2 different scopes, note that the aliases that you are generating for the Moon code, they don't have scoping. So if you have 2 in 2 different places in your program, 2 variables named x, then you must actually create some unique identifiers for your labels. One thing you can do, for example, if the function f contains variable x and the function f1 contains variable x also, then you can name them respectively fx and f1x, basically concatenating the name of the scope in which the variable is with the variable name itself. Thus you resolve this issue. So anyway, so you must make sure that whenever you're using labels in the Moon code, that these are unique labels. If they're not, then that's going to create runtime problems. And also important to note that here I'm explaining in the first part of the lecture, I'm explaining how to use this labeling method, where every of the things that you are assigning a value to, or you want to branch to or refer to, is basically assigned a label. Now you have to understand that if you want, especially if you want to execute functions, eventually you need, if you want to have one or more than one function to be executing at the same time, for example, if you have a recursive function, you're going to call the function, and then the function is going to call itself. So this basically, that means that it's going to be more than one instance of this function to run at the same time. If you want to allow that, then you need to have a space to actually contain the state of each of the different instances of function. So if you want to achieve that, then you cannot work with labels. If you work with labels, basically all the variables of a function are assigned a unique space in which they reside, or in which the state of the function resides. So if you want to allow that, which any programming language worth using would allow, then you have to use dynamic allocation using a stack, which I will explain in the later part of this lecture. So all this being said, in the beginning of the lecture, I'm talking about tags and so on. If this is what you want to do, fine. There's going to be a huge portion of marks for code generation that will allow you marks, which will give you marks if you're using the labeling method. But there's going to be also some marks for using the offsets method and the stack-driven method for function calls. So if you're using tags, that will prevent you from getting some of the marks, a small proportion, but still, if you use only labels, you cannot get 100% of the marks. Okay, so after you have assigned some value, some memory to this variable x, then the question becomes, how do I access this value that you will store in the computer's memory? Because if I can draw something here, so literally what's happening here is that you have the computer's memory, which is segmented like this, and eventually you have assigned, when you did this xres4, then you have assigned literally this to this memory cell in the computer's memory. You have assigned this memory cell here to this variable x. So then if you want to access this value, then what you do, you actually load word with regards to the label x, and then what you have here between the parentheses here is the offset. Note that by a convention, in all the code I'm showing, R0 is always containing 0. Why is it so? Because very often you're using the value 0. So if you don't assign it to a register, then you have to create a 0 every time, and tends to make the code longer. So for the sake of representation here, I'm using this convention that R0 always contains 0. Anywhere you see in the code R0, it means it's 0. I'm never using R0 for anything else. Okay, so here basically you use the address of X and then with offset 0. So basically you are referring here to this memory cell with offset 0. So that's basically this memory cell here. And what you do is you load a word, which is the entire memory cell, the entire binary presentation of something that is in this memory cell here. And you actually load that into register number 1. Okay. As we will see later, you could actually have, instead of having 0 as the offset, you could have a number as an offset. For example, if you'd have 4 as the offset, for example, if you would have load word register 1 X, and then let's say in R1, you would actually store, say R1 is equal to 4, you would store R1 into 4 into R1, then you have to offset 4 with regards to X, which will actually point to this memory cell here. So if the value of R1 would be 4, then you would actually be retrieving this word here. So that's what we're going to do later on when we use offsets to refer to aggregate data types, or value of aggregate data types. Eventually, if you want to actually store, here this was to retrieve the value from this memory cell. If you want to store a value in this memory cell, then you actually use a store word, and you refer again to the alias X with offset 0, and you take the value that was in your register number 1 and you push it into this memory cell. Whenever you have in a register is also 4 bytes. So that's why my examples are conveniently using this notion that the values I'm manipulating are assumed to be integers, and the assumption is that an integer is actually 4 bytes, which happens also to be the size of a register. So here, the X in light blue refers to the alias that you have, the aliases that you have in the Moon code. The X here in green actually refers to your variable X in your source program. And then the R1 in dark blue and R0 are basically registers. So we have 15 registers from 16 registers from R0 to R16, R15, sorry. Okay, so what if you have a declaration of an array of integers? Let's say an array of 4 integers. That's basically that if you store that in the computer's memory, eventually, as I exemplify here, if you have an array of 4 integers, then it's basically assuming that each integer is stored in a contiguously allocated memory block. So that's basically here in my example I already had, that my array would actually be stored here, and that would eventually be A. That's my array A. That is the result of reserving 16 bytes. Okay. So how do I then push some values or retrieve some values from this here? So you see that the only thing I have, the only name I have to refer to this is A, and A is actually referring to the, or it's actually an alias to the address of the first memory cell. If I want to access this one here, I can refer to A with offset 0, but if I want to refer to this, then I have to refer to A with offset 4, and so on and so forth. Okay, that's what I mean here by here. This is A, and this is A of 1 times the size of an int, which is 4. A plus 4 is, or A with offset 4 is actually second element. A with offset 8 is third element, and A with offset 12 is actually the 4th element. So that's eventually what you have to do when you refer to the elements of an array. You have to use the size of each of the elements In the case of an integer, the size is 4, and you basically build your offsets in order to refer to each of these elements to either fetch the values from the memory or to push the values into the memory. So for example, if I want to generate code for x is equal to a of 2, so basically that means I should get a of 2 being this one here. So basically I need to have the a plus 4 is 8. So a with offset 8 is actually the value that I want to get when I refer to a of 2. So what I basically do here is I generate an 8 from scratch. So how do I do that? I use the add I or add integer, which has 2 operands, which are the value in a register plus an integer value. Here I'm basically taking R0, which is 0, as a convention. I mean, I could put other things in R0. Okay? It's not that it always contains 0, but as a convention for me, when I give my examples, I always keep R0 at 0. I will never use R0 for something else. So R0 contains 0, and then I add 8. So that's basically what I put into register number 1, which then is what I use as my offset when I refer to A. So that's basically pointing to A here, and then adding 8 as an offset, which is basically making it point here. So for example, a R1 here, because R1 is 8, then I'm actually pointing here. And then I'm taking this value and then putting into register number 2. And then eventually what I'm doing is the assignment. I'm assigning the value of this to my variable x. How do I do that? I take the value that I just stored into register number 2, and I put it into the memory cell that corresponds to x with offset 0. So basically I put what I got into a of 2 into the cell that corresponds to x. So that's basically a very good example to show how do you get and put using offsets or not. So the same thing goes if you have multidimensional arrays. It's just that you have to then take into account that not only have a linear allocation, you also have a multidimensional allocation. So essentially what you do is, as is done in C and C++ and many other languages, so basically if you have a 2-dimensional array, essentially you have a 2-dimensional array like this. So then basically you consider that, well, depending on which side you see things, you consider that this here is the first row. This here is the second row, which goes after the first row, and this here is the third row that goes after the second row. So you basically linearize this multidimensional structure that you have. And this is the formula that you would use if you want, for example, to refer of A of 1, 3. If you have this array here, then you basically point to A, and then the offset is 1 times the size of int times the number of columns, which is 3, plus 3 size the number, the size of an int, which is the 3 that you are asking for here. So you need to actually encode this somehow when you want to refer to the elements of an array. So that's what is somehow more complicated when you actually use arrays and you want to do some computation using arrays. So it always involves that you have a little bit more code to actually somehow implement a formula like this to actually compute what is the corresponding offset that you have. Of course, the more dimensions you have, the more this formula is going to be bigger. That's going to lead your code to be much longer. But keep in mind that you are, using some automated code generation that is going to use some kind of algorithm to automatically generate this code. Okay, so once you have the formula figured out for n dimensions, then it's going to be, the problem is to figure out what is this formula and what code it actually generates. Now, these two examples were for arrays of integers. Now, my assumption here was that one integer was actually stored in one memory cell. So what if the elements of an array actually are, each of the elements are contained in more than one memory cell? So let's say, for example, you have a floating point number. So the assumption, for example, might be that floating point number would be stored in two consecutive memory cells. That's one of the things, there's no such thing as floating point numbers in the Moon machine. There's lots of different ways you can actually encode them. One of the difficulties is to actually implement the operators. So if you have a specific encoding for floating point numbers, then you have to implement, for example, your times operation. How is it done versus the encoding that you have? You may want to see inside of the source code for the Moon machine, there's a particular library that actually implements the floating point numbers. Not that's the only way to do it, but that's if you want to use this, go ahead. Okay. So all this to say here, we're talking about you're creating an array which contains atomic elements which are not stored into only one memory cell. So of course, then what's going to be happening, for example, if you have an array of float, taking the assumption here that a float would be stored in two consecutive memory cells, then eventually you have to reserve two memory cells for each of the elements. So that's basically going to create double the size versus an integer. So for example, if you have an array of 4 floats, if each float is stored into 2 words, then you would have to reserve 32 bytes for this array of 4 floats. And basically what you have to do when you compute your offsets, then of course you have to take into account what's the size of each of the elements. Same thing, well, I'm about to explain also how to do, what's the concept of objects as aggregate data types and how you use offsets. Well, there's also compounding the notion of arrays of objects, okay? Arrays of objects are more complicated because it involves that there is 2 levels of abstraction of offsets. There's the offsetting to refer to the elements of an object, but then if you have an array of objects, then you must access the right object using offsets relative to the size of objects in the array. And then when you get the object itself, then you must use another offsetting to refer to one of the elements of the object itself. So arrays of objects appears that it's very complicated, but once you figure out how to do offsets, it's not that complicated. It's just one more thing you have to do. And that's one of the things about this assignment number 4 is that it's not necessarily that it's very complicated to do. Once you actually figure out how to use this Moon code, this Moon machine, and you successfully can generate a program that you can execute, then you basically have a lot of different things to do, as you saw from the list of requirements in the assignment number 4. So it's not that some of those things are very much more complicated to do than the others. There might be some more complicated elements to implement, but the real difficulty is that you have a lot of different things to do, and you have to make a choice as to, if you don't have enough time, you have to make a choice as to what is worth more your time, the time that you have. Okay, so what if, for example, what if I have an array of 3 by 4 integers, and then you see my example here, one of the previous examples was doing an assignment like this, okay? But what if you have a 2-dimensional array? Okay, so essentially here, what's going to happen, and also what's happening if you have what you have as indexes is not a number, but is rather an expression, because the indexes can be expressions. So we will see how to generate code for expressions later, just taken for granted that we have the code for expressions at this point. So of course, when you see this declaration here, the code that you will generate is reserving 48 bytes for this here, which is 3 by 3 times 4, which is 12 times 4 for each integer is 48 bytes. Note, I will repeat again that if you put memory reservation inside of your executable code, this will eventually make your machine crash. So when you see a res that I insert in the code, basically the code that I'm listing here is sequentially the code that you are generating. Eventually, if you look in the project, here, if you look into the project, eventually you will see, let's say, tag generation, code generation, tags based. So eventually you see that, okay, so you have two streams in which you are generating code. You have Moon data code and you Moon exec code. So that's the way I use to actually make a separation. What you want eventually at the end, or maybe I can show, let me erase the whole thing. What I can show is the output of some of the, let's say, tags. So that's my output code for this example. As you see, if you go at the end, you see that, well, first of all, program starts with entry. So that entry is the first thing that's being executed. So even if you have some more code before entry, this is basically the entry point of the execution. So you're going to start executing. So why do I have code here? It's because some of my functions were declared or defined before the main function. So that would be the code for my functions that were defined before my main function. So as you may see here, I have my function f that was defined before function main. Here I have the code of my function f. And then here, eventually, I have my, where's my entry? My entry is here. Entry is basically the start of the execution of my function main, or in my slide, it's called a function program. So that's my code for my function program. And then basically it ends, the execution ends, execution of the main function ends with halt. It starts with entry and then ends with halt. If this is basically executable code, and the machine will actually increase its pointer and execute each of these things here. It's going to want to execute each of these instructions. So that's why if inside of these instructions you put something like this, a res, then it's going to want to execute some data, which is more likely is going to fail. So what you want to do is basically whatever you have some reses to reserve some memory, and you basically don't put them with the code. Okay. So you make sure that it's not going to be tried to be executed. So that's why in my code generation, I actually have data and execution, data code and execution code, so that I generate my code. If I can go back to my slides. Oops. So when I generate my code, it's going to be really generating this and then going to be generating this, because all the code is going to have to be generated sequentially. However, you don't want to put these res inside of the executable code. So that's why I output it to a different stream. And eventually at the end, I have the instructions stream, and I have the data stream. And then I take the instruction streams and I append it with the data stream after the actual halt. That's how I avoid that I achieve that I can generate my code all sequentially, including data and execution code, and then I separate it and I append it later on. I append the data after the data part after the execution part. Okay. So here I generate the reserve. When I see the variable declaration, I generate the reserve. Then eventually, so here's basically your abstract syntax tree. So that's the abstract syntax tree of this piece of code here. So you have a variable declaration here, and you have your assignment statement here, right? So the way that this is showing is that this is basically the order in which things are being executed. So you see that 1, 2, 3, 4, 5, 6, 7. This is basically showing that this code here is generated sequentially. And what sequence is generated is basically when you traverse the tree. Remember, when you use the visitor, it makes the tree traversal, the depth first search tree traversal, and basically fires the semantic rules as it goes in this tree traversal mode. So eventually what's going to happen is that when I go to statement block here, it's going to basically call it to tell all its children to actually accept this visitor. And then when you go to a certain node, depending on what kind of node, it's going to be calling the method to actually implement your semantic actions for the code generation. So you see that what's going to happen is when you make this statement block visit, it's going to tell, use the visitor, the code generation visitor. It's going to tell its two children to actually use this visitor. Then when you have a number here that actually corresponds to the number here. So this variable declaration node here is going to be responsible to fire a certain semantic action that is going to generate this code here. So you see that this variable declaration node here in the in its children, it actually has. So what are what's the information you need to have into your hands in order to figure out that you need to reserve 48 bytes? It's the type of this variable plus the dimension list. So the type is integer. That tells you for every element you need to allocate 4 bytes. So that's 4. And then dimension list is 3 and 4. So you go 4 times 3 times 4 gives you 48. So you reserve 48. So that's how variable declaration can be able to figure out how to generate this code here. So I'm going into all the details here, explaining the mechanics of this, but I'm going to assume that you understand it when I go in the later examples, which are almost all of them are going to be example using expressed using a tree like this with the corresponding sequence. So first thing that happens is you reserve 48 bytes. Then the next thing that should happen as you execute this here is you should evaluate expression 1. So eventually the visitor is going to fire here, then the visitor is going to fire here. Then, of course, the visitor is going to be fired on each of them here, but only those that actually have numbers here involved would actually be generating the code that I'm exemplifying here. So all of these are told to use this visitor, and eventually when you come to nodes of these specific types here, a specific semantic action is going to be fired that is going to generate code in a certain, so you see in a certain order. So you see, for example, this assignment statement is told to visit, but you see here that number is 7. So you might ask yourself, why isn't it 2? Because the first one I had was 1. How come I come here, it's 7? Thing is that if you look in the code, so visit, okay, so this is a good example. So you see, when you actually, if you are the program block node, or yeah, this one is a good example. So you have the program block node. So that's one type of node in my abstract syntax tree in my example. So you see that one of the things that it does, or what every kind of node should do, is to tell their sibling, their children, to actually also accept this visitor. That's why you have this for loop here that actually calls accept on all the children of this node. But you see here that in this particular node, before it actually tells their children to accept this visitor, it actually does something. In this one is a good example because it does something, then tell their children to accept this visitor and possibly do something. Then once all the children have finished, and then basically the tree traversal comes back up in the tree, after all of these would have been resolved, then it does actually something else. Okay, so that's how it can end up having things like this, where seemingly this one here does nothing for the moment, but just tell these children to accept and so on. And eventually, as it will come back, then a assignment statement will fire a semantic action that is after it actually has told its children to accept. Once they have all accepted, then it will do something, and possibly taking into as input some information that their children have generated as they have generated their own code. Okay, so how does it go? So accept is being propagated, then eventually accept. So all of these here will eventually call accept of their children before they do something. Okay. And then eventually it's going to get here, and this one is going to receive this accept and is going to generate the code number 2, which is the code for the expression. So you see here that the variable A has a index list, which is this index list here, and each of the elements is an arithmetic expression. So as the arithmetic expression is being, the tree is being traversed, as we will see later, the code will be generated for this arithmetic expression. And eventually, again, as we will see later, this arithmetic expression, the value of this arithmetic expression is going to be stored in a certain temporary memory cell that you will have allocated and that we assume will be named T1. Okay. So this semantic action number 2 will yield value T1. So that's what I have here also. So you can imagine that here, as if you would see the code that you would see at this point here is the code for the entire expression number 1 here. And eventually the last thing in this code would eventually store the result in the alias T1. And then when this is done, then it comes back here. And then after this one, if after this children has done the generation of its code, then it comes back here. And then you see that this node will do something, which is this here, to actually store the value that was just stored in T1 and retrieve it into register number 1. Then it will tell its other children to actually do the accept, and then this child will actually generate, or the subtree below this child would generate the code for expression number 2, which would yield its result in the variable or the alias named T2. Then eventually, when this is finished, comes back here. Then once this child is finished, then the code, the semantic action inside index list would actually be taking this result T2 and put it into register number 2. So essentially, register 1 and register 2, they contain the actual computed values of both of the expressions that define the indexes that you're using to refer to an element of A. So eventually, you have to implement this formula here, as I explained earlier. So if you have these values, you can actually figure out the indexes or the offset that you want to use. So essentially, you figure out that you want to use offset using this formula here, which these instructions here are basically making this computation, yielding the value into R5, which is then your offset. So that's why then if you want to access this element A of expression 1, expression 2, then this formula here has computed the offset that corresponds to this combination of indexes. So you refer to A with offset R5, which is the result of this formula here. And then you take this value, put it into R6, and then you take R6 and you put it into X. So you take this value here and you put it into X. So you see here that many things are happening here, which is the same kind of explanation scheme I will be using for all the remainder of the examples. So you have this sequential number here, which is really showing that this code is really generated sequentially as the tree is being traversed and as the different semantic actions are being triggered that will each generate a tiny bit of code, but all of this is going to be generated sequentially. Okay, don't think that this code is generated going back and forth. It's really generated sequentially. If you're thinking of going back and forth, you're doing it wrong. So it is generated sequentially using these numbers, and then I'm showing you the AST, abstract syntax tree, that corresponds to the bit of program that you have, and that's basically showing you which node is actually firing a semantic action that is generating this bit of code here. Okay. Another thing to understand, I will again repeat, there are some things that may happen before you tell your children to accept, or after you have told your child to accept, and after your child has done its code, and maybe after the child has done its code, then you fire an action. After this specific child has run its code, then you fire an action that generates more code that will go after the code generated by the child. Okay, exactly like we did here. So here we basically generated the code for expression 1. Then when the code for expression 1 is done, basically this was done after, or as the arithmetic expression child was told to accept, then the result is that it generates this code. And then you must, in between every child's execution, then you are loading every of the results into a register. Okay. For those of you who think ahead, then you might see, okay, so that basically means if I use the scheme of code generation, if I have, let's say, a 25-dimensional array, then this code is not going to work because I have only 16 registers. You would be right. Okay, that's one limitation of the code I'm showing here. Not that it's very important. I mean, you can deduct you marks if you can have less than 15 dimensions. But in reality, if you want to make it so that you can have n-dimensional arrays, then you would have to figure out a different way to generate the code, not using registers. Okay. Okay. In other words, I'm not claiming that the code I'm generating here is optimal code. There is some limitations, but at least the code runs. Okay, and that's what I want to see. At the end, when you do your presentations, I want you to be able to show that the code actually runs. Okay, so how do I deal with objects? So an object is very similar to an array. An array is basically a collection of data elements which all have the same type. So they have the same size. So it makes it easier to figure out what is the offsets, because the offset of every element is the same. However, when you have an object, the object follows this kind of blueprint, which is the class, which says if you have an object of type myClass, then its first element is an x, which is an int, and its second element is a b, which is an array of 3 floats, and then the third element is y, which is an int. So basically, you would reserve memory for an object of type myClass. You would need to actually reserve this amount of memory. You can take into consideration that an int is 1 word, a float is 2 words, and so on and so forth, which is an assumption that I made throughout my whole slides. Feel free to use your own assumptions, but that's the assumption I made. Okay, so every time I have an object of type myClass, it would have somehow this shape inside the computer's memory. And if I want to refer to the elements or the data members of the values of the data members of this object, if I want to refer to x, then I use a with offset 0, which is this word here. If I want to refer, let's say, to the first element of the b data member of my object of type myClass, then I would use a plus offset of x, plus the size of an x, size of an integer. So basically, a with offset 4 is the first word of the second, first word of the b element of my object. If I want to refer to y, then I need to have the offset. So that's basically a plus the size of the first one plus the size of this entire thing, which is then giving me the offset of my y member of my object. Okay, first thing, if I want to reserve enough memory for an object of this kind, then I basically determine what is the number of words or number of bytes that are consumed by each of the elements. So basically, I do a running total of the size of each of the elements, and that gives me the number of bytes total that I need to reserve for an object of this kind. So in terms of small example here, if I want to refer to an object of type myClass, A here, right, to refer to the second element of the array of float B, then that basically is, when I have a formula in black like this, that actually means it's a formula to compute an offset, just like we had these formulas here. These formulas for offsets will come later in many places, like this one here. So it is basically an offset calculation formula. So essentially, if I want to refer to a.b2, then I should refer to a with this offset here. So essentially, I need to generate code that will compute this offset. And then eventually, so you see here, I make this computation, and then eventually I put the result into R1. And then I use R1 as an offset with referring to an offset with regards to A. So then here I basically I'm referring to A with offset R1, which makes me actually point here. Then I retrieve this here and actually put it into X. Okay. Okay. So that brings me to say that if you want to compute the size of an object or the size of an array and so on, so you might have to do some computations. every time you actually implement the code. So one of the things you might do, which is actually what I do in my example code I gave to you, is I have this compute memory size visitor, which I've shown in class already quite a few times now. It's basically it basically goes over my symbol table elements and then computes what is the size of each of the elements. And notes, for example, the size of the variable x is 4 bytes, size of variable b is 24 bytes, size of variable y is 4 bytes. And basically it does a running total of this and then figures out that an object of type myClass is 32 bytes. So that when you actually, if you have this in the symbol table, then you don't have to compute it as you're actually doing your code generation. You just retrieve this information from the symbol table. It can be very handy and making it so that your code generation is somehow simpler. Also, it makes it so that, well, assuming that the data you have in your symbol table is correct, that you have less possibility of making mistakes, computation mistakes, as you implement your code generation. Okay, so that's for the compute memory size visitor that I have implemented. Contains the size of every element inside of a scope, computes the total size, and here what you have here is essentially the offset. So if you want to refer to an element y inside of an object of type myClass, then you know that the offset you need to use is 28. So that prevents you from having to implement this formula here in your code. So you can really use 28 here, which is something I will use later on in some of my examples. Okay, so how do you generate code for expressions? You see that this is getting more and more complicated, but also more and more interesting. So keep it simple. The first, the atomic elements of an expression is the operators. So what you should see as each of the operators is kind of a mini pattern of Moon code that you have in place that you need to generate. So it's always going to be the same pattern independently of what are the operands, of course. Okay. So for example, if you have a plus b, or you have a plus operator used onto operands, so essentially the pattern you will have is this here. So you refer to this alias a with offset 0, and then again, this is for computing integers. So you refer to a with offset 0, put in the value into R1, b offset 0, put the result into R2. So basically you've loaded the values of your two operands into two different registers. Then you use the add operator to add these two values and put the result into register number 3. Then what you want to do, because this operator potentially is part of an expression, okay? So you need to essentially, this is part of a tree, okay? And the plus node is one of the sub-node of this whole tree for the expression. So what you need to do is to expose this intermediate result in your tree to the node that is upward in the tree, so that this other node can actually use this intermediate result, or temporary result, should I say. So you create these temporary, you reserve some memory to store each of these temporary results that are necessary to have in your tree. So the higher is the tree, the more you have, the more layers you have in this tree, the more you have temporary results. So eventually, if you have longer expressions, you're going to have a lot of these, more and more of these temporary results. So you create a temporary memory cell allocated that needs to be allocated to store this temporary result. And then you actually store your value, that is the addition of your two values of your operands, and you actually store it into this memory cell. So that, for example, if this plus is part of bigger expression, then one of the operands of an operator on top of the plus is going to be able to use T1 for its own, as its own operand, essentially. So that's what you have to do. That's the mini pattern that you have to implement for anytime you have a plus operation. So you have to make these patterns general so that it actually applies to all cases. So it's not, you might generate a pattern that actually works if you have something of this kind, x is equal to a plus b. But you must also think of what's going to happen if you have x is equal to a plus b times c. So the pattern that you use must actually work not only in this very specific and simplistic case, must also work for when it's used in combination with other operators. And this particular pattern I'm showing here is actually achieving that, as we will see by examples later. Interesting, and what is simplifying your job here, if you see for the implementation of the code generation pattern, the times operation, it's actually exactly the same, except that you use a multiplication operator. If you are using if some of your operands are integers, you may want to use the operator add I, which is allowing you to pass as one of the operands directly the integer number that is being used inside as an operand. Note that this actually works only for integers. So if you are doing operations for things that are not integers, then you can't use add I. So essentially, it's kind of the same pattern, except that there's one of the operands you don't need to load it. It's actually you hard code it in the code as one of the operands here. Okay. So that's so you see that there's many different things which are very similar in these things. Concepts are very similar. If you have relational operators here, I'm showing only equal, and I'm not showing the greater than and greater or equal and so on, but that's roughly the same idea. Okay. So for the equal operator, so then here basically it's the same idea. You load each of the operands into registers, then you apply the equal operator between the two values of the operands that are now stored in registers, and then this operator is going to put the result into another register. So you basically, for implementing an equality check, you use the CEQ instruction of the Moon machine. So it's basically going to do bitwise equal of the two words. If it's equal, then it's going to create, it's going to say 1, and if it's not equal, then it's going to say 0. The result is going to be either 1 or 0. And then you again create a temporary result, and then you actually store your value into the temporary result. Similarly to what I said before, you also have a CEQI if you want to compare a certain operand with a literal integer value. Now, if you want to do logical operators, it's a little bit more complicated because there is and or somehow into the there is actually bitwise operators. So and Moon machine and Moon machine or is not the same thing as you understand as and or. It's actually bitwise operations. So that's why if you want to implement logical and logical not and logical or, and you must somehow hard code them. So here's how it goes. So you basically, again, load A and B as the two operands of your logical and you reserve a memory cell to store the result. Then here, this is basically a hard coding of a logical and operator. So here basically you use a branch on 0 or two consecutive branch on 0 on both of the operands. Why? Because if either of these two is 0, then the result is 0. Basically, if any of the two is false, then the result is false. So if any of R1 or R2 is false or 0, then you branch upon this here, which is creating a 0. It's basically adding 0 to R0, which is already 0, putting the result into R3. Then, okay, so if neither of these two are true, then you would actually create a 1 and then go back here and then allocate this 1 to, well, that should be R3 here. R3 would actually be put into T7. So that's a mistake here. I'm going to fix that after I'm finished this presentation. So instead of R0 here, it should actually be R3, I believe. Okay, all this to say that if you want to do a bitwise, if you want to do a logical AND, then you need to actually hard code it using certain structure of Moon code. Similarly, if you want to do a NOT, I'm not going to go into explaining this one here. That's kind of the same idea. Same thing for an OR. You need to basically hard code them. Now, what if you want to combine different different operators in one expression that uses more than one operator? So let's use our good old A plus B times C here. So essentially, if you have A plus B times C, you would end up having a tree like this. Okay. So you have the plus, which is applied to the A, and the second operand is the result of the multiplication of B and C. Okay. So you see here that the code that's being generated is in this order here. So you basically generate the code for B times C, and then you would, after this code has been generated, then you would generate the code for A plus the result of B times C. Okay. Remind you, how do you make this one trigger before this one? So basically this one would come here and then tell both of these children to visit before it generates any code. Then this one would do the same. Then once all the children of this one would have been triggered, then when it comes back here, after it has told its children to visit, then it starts generating code. And this one is organized in the same way also. So that's why the code is generated first by this one, and then second by this one. If you want code to be generated before the children are being visited, then you include your semantic actions before you make the calls for your children to visit. Okay. No, I'm repeating here, but these are things that are important for you to understand. Okay, so essentially, if you remember what is the code pattern I've shown for the times operation and the plus operation, you will recognize here that this is exactly the same pattern I explained for the times operation. So my times operation was here. So this is the code pattern here, and you will certainly recognize that it's exactly the same pattern as you see here, except that I'm referring to the operands that are specifically in the tree here. Of course, here you must understand that when you're generating temporary results, you must have some kind of label generator. It's going to be like creating, here I'm using T, like T1, T2, T3, and so on. So you should have a label generator that's going to generate variable names for each of these temporary results, unique variable names. So essentially here, this multiplication code generation for the multiplication operator was triggered, and is yielding its value in the memory cell named T8. And eventually what this code is going to do is to add A to T8. Okay. You see it loads A, loads T8 into R1 and R2 respectively, puts the result in R3, and then puts R3 into T9. So for example, if there would be Z times A plus B times C, then the higher level operator would actually use T9 as one of the operands, and so on and so forth. So that makes it so basically that once you have this way of doing, then your operators, your expressions, no matter what's the size or the complexity of the expressions, if it's well organized, it's going to work for any expression. Now, yeah, that's exactly what I was trying to explain here now. What if each of the different operands of your expression are themselves expression? So that would be, if you do things correctly, as I explained, then it's not going to be any more complicated to actually do it for more complex expressions that are essentially expressions that are composed of other expressions. So eventually, if you have something like this, then you're going to have the add operation. And then here, this entire subtree here, you're going to have the code being generated for this entire subtree here. And then eventually you're going to go here, and then you're going to have the code for this entire subtree here. And then you're going to go here and generate the code for this entire subtree here. This subtree is going to yield its temporary result in T2, this one in T3, and then the code you generate here is basically adding T2 to T3, expecting that these results have already been computed, okay? And that all the code that was generated by each of these here is working properly if things were done correctly, as I've explained earlier. So all this to say that if you do things correctly in a well-organized manner, it doesn't matter if the expression is complex or not. Okay, if you do it as I explained here correctly, then it should work pretty easily. Now, even more interesting is what if we have statements? So I have given some examples about assignment statements. So assignment statement is basically taking a value and then pushing it into a memory cell. So up to now, what we saw is that we are using the values. We were using LW to load words and use them as computation arguments for operators, essentially. Arguments of operators. Now what you're doing is you compute a value. When you do an assignment, you compute a value and then you push it using SW to store this value into a memory cell. For example, if you have A or assign B to A, and you basically load B, put it into register number 1, and then you actually push using SW or store word. You take this value that is in this register and you push it into the memory cell named A using offset 0. Of course, if you're pushing into an array, then you would need to actually use offset, which you would have to use a register, compute the offset, put it into a register, and then actually put this value, which is your offset, inside of this here. So that's how you would assign to an array element. So that's pretty standard. So that the key here is that you basically store a word, store a value. So you see that assignment statements are pretty easy. Not so easy, but not so more difficult is a conditional statement. So here what you start to have is branching. If you want to do conditional, it's basically that you have branching in place. So then you must generate code that will somehow hard code the branching. So the only thing that you have in assembly language is you have branching. It's like, for those of you who've heard about this evil go-to statement that you used to have in some programming languages that allowed you to basically branch anywhere in your code. That can be very handy, can also be very confusing. Okay, so the branching of an assembly, the branching instruction of an assembly language allows you to branch anywhere in your code where you have identified a label. Okay, That makes it very chaotic if it's not well used consistently or used with control, if you might say. So, so how do you use it correctly for doing the implementation of a conditional statement? So essentially, you evaluate this expression here. If this expression resulted true, then you execute this block here, and then you skip this block here. But if this is false, then you skip this block here and execute this block here. That's basically what it means. And that's exactly what the resulting Moon assembly code will do. So you see that sequentially, there are these semantic actions that are triggered that are sequentially generating this code here. And that's in terms of the tree, that's the order in which these semantic actions are executed in each of these nodes. So you see that one is generated by the relational expression subtree. Two is executed after this one has resolved, is called to accept. Then the if will tell this child to accept, which will result in creating this here. Then after this one resolves, it's called to accept, then it will actually fire some rule that will generate this code here. Then it will tell its other child to accept, which will generate this here. And then after this one resolves, then it will generate this code here. Okay. So you see that this is an interesting one in the sense that you have to properly orchestrate the order in which each of these semantic actions are, where they are placed and when they are fired, so that they actually generate this sequence exactly. So what is the code that you are generating? First, you generate the code for the expression. If you come to an if statement, there's no question about it. You are executing this expression, the relational, well, it doesn't need to be a rational expression. It's an expression you evaluate, and you want to know if it's true or false or 0 or 1. So when you come into this if statement, you execute the expression, and you try to see if it's true or false. So first thing you do is you generate the code for this expression. So we saw earlier in the previous slide how to generate code for an expression. It is then going to do exactly the same, generate code for an expression, and it's going to yield its result as in the alias tn. Then the first thing, then the next thing you want to do is, if tn is true or false, you'll do your branching accordingly. So you load tn into register 1, and then you use this branching on 0. BZ means branching on 0. So if the value in R1 is 0, then you go to else 1. Essentially, you skip stat block number 1, and then you go to you branch onto else 1, and then start executing code block 2, and you eventually get out of this if statement. So the result is that in this case, you evaluate the expression. If it's false, then you skip this, execute this, and then continue. You basically skipped over this code here. If it's not false, then you would actually not branch, and you would execute this here. And then when you come outside of this block here, you have this J here, which is an unconditional jump. There's no question about it. You will jump to this here. If you see J something, there's no question. You just jump to this label. So you jump here. So you basically skipped statement block number 2. And that's how you organize your if statement. And you see that if you put these code generation semantic actions here in the right places, and you fire them in the right order, then it's going to generate sequentially all of this code here. Let's go to the next one, which is a loop statement. So you see that once you understand the notion of the jump, and that the notion that you should generate all of this sequentially, and that the job is essentially to create. So you see that all of these semantic actions here, for example, 1, or let's say let's take 2. So this semantic action 2 here, when it's fired, it actually generates this tiny piece of code here. Okay, it's not that this is complex. The complexity becomes to be able to generate simple bits of code that actually work together. Okay, and that they are fired and put in the right places at the right moment. So the code you generate is not necessarily, each bit is not complex. It's just that you have to make all of these bits of code to work actually together so that they're placed in the right order and none of them are missing. Okay, so for the loop statement, so here we have a while statement. So again, to express what is the notion of a while statement, you have while expression. So when you come into this while statement, you start right away by executing this expression. If it is false, then you skip the block of the while. If it is true, then you execute the block of the while, and then you unconditionally branch back to the start where you started executing or evaluating the expression, the conditional expression. Okay, so that's exactly how it's organized. So you have this while statement that has an expression and then a statement block. So the first thing you need to do, in this case, you need to be able to branch back. So the first thing you generate in terms of code is a label that allows you to here jump back to this label and do another iteration. So note that you may have several whiles in your code. So again, you need to have a label generator that's going to generate while labels. Here I'm using essentially, I'm assuming that it's using while 1, while 2, while 3, and so on. So you could, for example, have in your implementation of your node here for the while statement, you can have a label generator inside of the class of this node. Okay, so first thing you do is generate this label and then put it here so that you can later on branch back. Then once this has been done, so you see here that soon as you enter the while, as soon as the while statement node is told to accept the visitor, first thing it will do is to output this code here. Then it's going to tell its child here to start generating the code. So it will tell its child here to accept this visitor, and that it will then tell each of these, the children of these nodes are going to be told to accept, and that they're all going to start generating code until they're all finished generating this code here, which is the code implementation of the evaluation of the expression in question. And it's going to yield Tn as a result. Then what you need to do is use some branching to either execute yet another iteration or skip over the entire block if the result of the evaluation of the expression is false. So you load Tn into R1 and then branch on 0 R1. If this expression is false, then you branch onto end while, which is another label that you must generate, which is at the end of the code of your statement block for the while. So if you branch here, you basically skip this code here and you come here, and then basically you would continue generating code for the next statement. So basically you go to the next statement, the execution of the code of the next statement. Then if it's not 0, then you execute the code of the statement block. And unconditionally, inconditionally, if you come here, then you will conditionally branch back here, execute the expression again. If it is true, execute that. If it is false, then you basically end the iterations. So you see that it's the same concepts, It's just a way to organize your code so you have branching, conditional branching, and so on and so forth. Now, what if you want to input some things from the keyboard or output some things in the console? So that's one of the things that are tricky with the Moon machine. The Moon machine is extremely primitive, so it does not have like a cout or anything like that. So it can be quite a very low-level thing to implement just to output something on the console. For example, if I can show this here. So this is my console. So I basically compiled. So I have my Moon machine here, the moon.c here. So just to show you, I've used GCC to compile the Moon machine here into an executable named Moon. Gave me some warnings here, don't care about those. Then it generated my Moon machine here, which is my moon.exe. Then I can actually execute. So that's I have created this program at the end of the slide set, which is slide 12. So if I So if you go at the end of the slide set, you'll see that there's an example for executing using a function. So that's the code that you will see on the slides here. So that's the code I'm actually executing here. Then if I want to execute it, then I use this here. So I go moon, slides12.moon, which is my code that I have on my slides. And I'm also using this library lib.m. If I execute that, and the only thing it does show is that it's loading these, and then that's the output of my program, and then it tells me how many cycles it took to execute this program. So that's my output. So if you look into slides, you'll see that into the meaning of this program, you'll see that the function f that I'm calling should be actually outputting 7, and the program function should be outputting the value 17. So you see that I have 7, 17. Okay. You could have put some strings here to say function f is outputting 7 and so on and so forth, but you cannot have this. We don't have the syntax for this in our language. So that's something we could do using the Moon machine, but it would be immensely more complicated. All this to say that there's ways, if you use write and you code it correctly, then it will actually output numbers here, which are the values that are being computed if you use the put or the write statement. Okay, so if you want to be able to demonstrate that your computer, that your Moon code is executing correctly, you should be able to use the write statement to show that the correct values are being computed. Okay, so it's actually very important for demonstration purpose that you have at least write. Read is not necessary, but write is very important to demonstrate that your code actually correctly works. If you don't have write as a statement implemented, then you can actually execute your code in debug mode, but then that's a much more tedious way to actually demonstrate that your program works. Okay, so read and write. So essentially what's involved here is that if you want to read or write, you need to be able to interact with somehow the operating system. Now, not to say that the Moon machine interacts, Moon machine is a C program, so it's essentially using C instructions to, for example, get something from the keyboard, okay? But that's a little bit cheating here. If you really implement a language that is not running onto emulated using another programming language, then eventually when you read from the keyboard or write to the screen or interact with a network socket and so on, you need to interact with operating system primitives which allow you to do that. Okay. So what what we have in our case is inside of the Moon machine, you have put C and get C, which are two very primitive instructions that are bitwise operations. Okay, so if you want to read an integer or write an integer, then you have to write subroutines that would eventually use put C, which are bitwise operators, and would output an entire integers, which is a series of bits. Okay. Luckily, there is these two libraries that some people wrote over the years, lib.m and util.m. As you have seen in my little presentation here, I was actually using lib.m. Okay, so I went here, Moon, and then execute this program and also use this other thing, which is a library. It's basically linking these two things together. So lib.m is implementing some functions, some subroutines that I'm actually using in my code generation, which I will explain right away here. So, okay, let's go to the example here. So what's eventually happening here is that you're calling subroutines. So the two subroutines that you are calling are defined into the lib.m library. So you're using put str and int str. Str is transforming an integer into a string. And then put str is outputting to the console a string, outputting a string to the console. If you want to output an integer to the console, you must first transform it into a string and then output the string. Okay. So essentially, you are taking, I'm not going to explain all of it, but I'm just going to explain the concept as we go. Okay. So let's say you want to output the value of tn. Okay. So your code here has, so you're writing an expression. So this expression can be an entire expression. So you would eventually generate the code for this entire expression yielding value tn. Then you want to write this value, the result of your expression here. So you're basically taking tn and then you put into a R1. So you see that's the same things as we used to do, except that here you want to pass this value into a subroutine as a parameter to this subroutine. Okay, it's kind of going forward here into how I will explain later that you're actually using some stack frames. So the idea is that these subroutines are expecting the values to be stored at a specific relative address. Okay. So the relative address that where this int str subroutine is expecting its value to be printed is the -8 address relative to its own function called stack frame. Okay, so the function has a stack frame in which it is executing. It's basically storing its state, its values that it's using. Inside of this stack frame, there is many different values. The values of the value of the parameter that it wants to print, it assumes it's at address number -8. Okay. Why is this minus? Because it's basically assuming that your stack starts at the bottom, at the very bottom, or the highest possible address that you have in your computer's memory for the Moon machine. This is the bottom of your stack. And then as you're using the stack, you're going up. Thus, the addresses are going down as you're going up because this is a maximal address. Okay. So basically, it's assuming that at some point in time, it's going to be executing here. Its stack frame is going to be here. And then inside of this stack frame at offset number -8, it's expecting that its parameter, the value it wants to transform into a string, is actually stored at this address, which is -8. Okay. Then after you've put the argument, because that's what you just did, you're going to call this this int string subroutine. its argument is stored at the address in its stack frame, address -8. So now you've given the argument to this function that you're going to be calling. Another thing that it does in its implementation, it uses a buffer. So it needs to know what is the address of this buffer. Okay. So now what you need to do is to actually give the address of this buffer to the function. So essentially the address of the buffer is a second argument that you have to pass to this function before you call it. The idea is that you're creating this buffer here and you name it buff. Here I have reserved 20 bytes for this buffer. And essentially here what I'm doing is I'm passing the address of this buffer onto the stack frame of this function in str at address -12. So basically I'm putting the value to be printed, and right above it I'm putting the value of the address of the buffer that is used in the implementation to transform this integer into a string. Then I am actually calling this subroutine. So the subroutine's name is intstr. So basically I'm jumping to this. And what is JL? The JL basically is jump and link. So what you want to do here is that you want to jump to the code that corresponds to this subroutine, execute the code in this subroutine, and then this subroutine at the end of its own code is going to have the corresponding JR or jump to register instruction, which is basically going to make it so that it's going to branch back right after the JL that we have here. So jump and link basically means you jump to this address here, you execute code, and then when you're going to encounter, next time you're going to encounter JR, then you're going to branch back to the code right after the JL, the previous JL that you had. Okay. That's the concept. Eventually what's happening is that you're storing the address here into this register, the address of this instruction here. You are storing it into register 15. Eventually when you do JR, then you're gonna actually you're gonna retrieve this value, and then you're gonna use it to actually branch back to this address here. Okay, we're gonna come back to that when you explain how to do function calls. We're gonna use JL and JR. Anyway, so that means here, this instruction, after I pass the parameters to this subroutines, which is the value to be printed and the address of the buffer to be used, then I jump to this subroutine, and then this subroutine is going to execute itself. It's going to put its value. In fact, and that's another important thing that you need to understand. This intstr or in string subroutine actually puts its value, its resulting value, into register 13. That's how it works. It outputs it does its computation and outputs its value in register 13. So if you want to use it later on, such as we did, we will do, you need to retrieve it from register 13. So that's what we do. We call this int str. It does its job, stores this result in register 13. We come back here, and then we get register 13. And now what I'm doing is good, because now I'm going to actually use put str subroutine. So put str is expecting to receive some parameters also. Where is it expecting to receive this parameter? It itself is also, by coincidence, expecting its parameter to be passed in the address -8 inside of its own stack frame. So you see, to receive both of these methods, by coincidence, expect their parameters at the same address in their stack frame. So I take our 13, which is the result that's given to us by this subroutine that transformed our integer into a string. Now we want to output this string to the console using putstr. So we retrieve the value, the int value, the string value, and then we put it into the place where putstr is expecting it as a parameter. Then we actually call putstr. So you see that this one uses only one parameter or argument. So we call putstr, then the result of it is that our number will now appear on the console. Then once this is done, then you continue the execution. So basically here, this whole code here that I have here is the code that I should generate when I implement the write statement. So here I've again put a tree here explaining sequentially what are all the different parts or different types of nodes that are involved in creating each of the different parts of code here that are to be executed again sequentially. Okay. So the order should be like 1, 2, 3. So you see that right away when program block, as soon as you come into program block, you should generate the code 3. 3 is what? Is the entry. Okay. So as soon, of course, as soon as you enter program block, which is this here, then you should generate the entry point of the program before you generate any other code. That's a very good example here of some piece of code that is generated before you generate other code. And 3, 4, 5, 6, 7, 8. So that's, you see that you have to think about it as to how you will organize when the code generation pieces of code are going to be inserted relative to when the children of the node are being told to accept. Okay. Okay, so that's it for the write statement. For the functions, okay. Okay, so that's it for all the statements. Now we're going to talk about functions, and that is where everything is gonna, I might say, gel together. Okay, so all that, everything we saw up to now is expressions, variable declarations, expressions, and then statements that are using expressions. Now, what we're going to do, well, you know, you could generate code, for example, for a program that does not use functions. Okay, if you want to go ahead and you don't have enough, you don't have much time to generate code, then you could generate code only for programs that don't use functions. Basically, that you have a main function. It has statements, possibly conditional statements, loops, and write and read, but never can you execute programs that define or call functions. So, you know, that's what I suggest that you do, that you start with something simple, then you see if you have enough time to do more, then you do more. Okay. If you try to do everything in one shot, it's likely that you're gonna end up coming at the end and you cannot generate code for anything that actually works. That you can generate code, but none of this code can actually be executed successfully using the Moon machine. All this to say that, as I will come back later at the end of this lecture, I'm going to tell you the advice is that you start with things simple and then you do a little bit more and you make sure that it works at every step of the way. Of course, one of the last things that you should attempt would be functions. Okay. As you will see, once you understand how it works, it's not that much more complicated. It's the same concepts as that we saw before. Okay, so it's basically branching and passing information around. So there, essentially, when you have functions, there are two essential parts when you translate code for generate code for functions. translating function definitions, or and then you're translating function calls. So function definitions is essentially, what is a function definition? It's a code block. Okay, it's a code. So we saw how to generate code for a code block. Code block is essentially a list of statements. So we saw already how to generate code for a list of statements. So eventually a function definition is a list of statements that you can branch onto and start executing them. Okay. So essentially when you call a function, you're branching to the code generated for these statements for this function. It becomes a little bit more complicated if you want to pass parameters to this function. So as you call this function, then you need to pass some values to this function so that it uses values that come from the exterior. Just like when we were calling the two subroutines here. So we were actually passing some parameters to these subroutines. Here we were passing the value to be printed. We were passing the value of the address of the buffer as a parameter that when it executes, and depending on what value you passed, it will actually process something different or proceed differently in the processing. Well, okay, so one of the difficulties, so generating the code for the statements, we already saw that. The additional difficulty is, well, how to do the branching, we already saw that also. The difficulty is how do you generate code for passing the parameters and passing the return value, okay? So there are different ways to do that. So I will basically show here how to do it somehow statically and eventually, well, which is the correct way, how to do it dynamically. So in the first way, I'm explaining how you can branch to functions and then reserve some memory for the state of the variable of the function, of the variables inside of a function. You can allocate these values statically by basically using a res inside of the code generation of the function itself. So you use a res along with, which is reserving some bytes, and then you identify this res with a certain moon label, as exactly as we did before. So basically for every of the local variables inside of a function, you would use a res to reserve memory for this particular, the value of this particular local variable to a function. Now, of course, if you know your stuff, you will realize that this is creating a situation where there can only be one function instance running at the same time, because you're literally statically allocating the values of a function. If this function is calling another function, which is then calling back to this function again, then you would need another memory space to actually store the values of this instance of the function and the values of this other instance of the function. If you're using tags, there's no way you can actually do that. So I'm going to show how to use tags because it's more simple to understand. Some people might want to stick with that. It's not a problem. There will be some additional marks to use a dynamic way of memory allocation for functions, but you're going to have a very large bulk of the marks if you're using the tags-based method. Essentially, also, if we can go to my example code. So you see that there is a tags-based code generation visitor. That is the method I was just talking about. And then there's stack-based code generation visitor, which is generating code that is dynamically allocated, allocating, essentially using a frame stack, a function called frame stack. Okay, so you have two different ways of doing. Arguably, it's more complicated to use a frame stack, but once you really understand how it works, it's a little bit more complicated using the frame stack. Okay,
So the code that you have to generate, first you have to generate code inside of the function so that the function receives its parameters. Depending on what parameter passing mode that you're using, there might or might not be some processing to be done to receive the parameters. I'm not going to go into all the details of different parameter passing schemes. Essentially what you're going to do, what I'm showing is pass by value. Okay, you could have pass by reference, there's a lot of them. What I'm going to do is pass by value. Then you must also do the reserving a memory for the variable declarations. So how are you generating code for allocating memory to the local variables to a function? You can do it statically, which I will show first, or you can do it dynamically using a stack frame, which I will show in the second part. Also, the execution code for all the statements is generated, which is what we saw before. And then once you finish the execution of the entire function, or you encounter a return statement, then you must make sure that this value, the return value, is going to be put somewhere in the memory where the calling function can actually fetch this return value. Okay, so you see that most of the difficulty compared to what we saw before is about passing the parameters, receiving the parameters, and then passing the return value. And somehow the branching. Okay. So you can actually store inside of your symbol table some of the labels that you'd be using if you're using a label-driven execution mode. So for example, for every function that you may have, you may generate a label for this function that is the label that you're going to use to actually branch upon to actually start executing this function. So this label can be generated as you generate the symbol table. Or you may have another visitor that's going to generate the labels later on after the symbol tables have been created. So of course, then after you have as you are to call a function, then there should be some semantic checks that will check if this function, let's say this function name exists in this scope, is available in this scope. If so, then are you calling it with the right number of parameters, the right type of parameters? So this semantic checks should all have been done in your assignment number 3. Okay, and then you would branch to this function only when you have established that it is actually this function you want to use and that it is actually properly called. Okay, so here I'm going to explain how to use statically allocated local variables, or by using Moon labels to identify every of the local variables inside of your functions. Okay. Not that this is something that you would do in real life, but I'm actually putting this out there so that if people are short in time, they might actually use this method, which is arguably more simple. So here's how it goes. So let's say we have a function definition like this one here. So this is the return value, this is the name of the function, the 2 parameters, and then some statements, then a return statement, and then some other statements. I know it doesn't make sense to have statements here, but that's just to explain that among the statements, there might be a return statement. Okay, so how would you generate code for this here if you're using the label-driven method or static allocation method? So one of the things you want to have is to have a allocation for the return value and the parameters of this function. Okay, so this function is going to receive some parameters. So it needs to locally actually store these values. So before the function that is calling this function is going to branch, then it's going to put these values of the parameters inside of these memory cells, that when you branch upon this function here, it basically assumes that these values have been copied into these memory cells. It's basically expecting its parameters are already there. So the first thing you do, as you see here, sequentially 1, 2, 3, 4, 5, 6, 7, this is the code that's being generated. First, fnres is a label that is storing, will be used to represent a memory cell that is used to store the value, the return value of this function fn, hence its name fnres. So eventually, when you generate the code here, you'll see that when there's a return statement, one of the things it's going to do is to copy the result of the expression into this memory cell here. Okay. So first thing you do, you see function fn, you generate you allocate memory statically for storing the resulting value when this function is returned from. Then as you process each of the parameters sequentially, or as you go into the fparams list, in each of the fparams subtrees, then you will generate the code to allocate memory for each of the parameters to this function. Okay. So once you've done that, then you have the memory that was allocated for the return value and the parameters to this function. Then the next thing you do, before you actually start the generation of the code for the first statement, then you should generate this label here. That is the label you're going to use to branch upon this function. Okay. As soon as you finish processing the fparams list, before you process any of the statements here, then you generate this label fn. Then you, as you go into the children of this statement block here, you have statement, 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 statement. You just basically generate the code for all the statements sequentially, as we saw before. Okay. Then eventually you're gonna potentially run onto a return statement, which is one of the statements we didn't explain before, if you if you notice that. So when you hit a return statement, what you do is, well, you return the value of an expression, as we hinted at before. So you would generate the code for the expression. Then you would, assuming that its value would store in label tn, then you take tn, put it into register 1, and then you take register 1, and then you put it into fnres, which is the memory cell you allocated to store the result. And then you go JR, which, well, if you remember, as I explained JL before, JR is the sister of JL. So you use JL, makes you branch somewhere. For example, you would use JLFN. So then you would execute this here, and when you see JR, then you would jump back to the instructions after the instruction after the last JL that you saw. Okay. In fact, it's a little bit more complicated than that. When you call JL, it's like JL R15, comma a label, and then JR R15. So R15 is basically a register that's being used to store the address from which you have executed the JL. So that when you go JR R15, it retrieves the address in R15 and then jumps back to the instruction after this address. Okay, so the jumping address is actually stored in R15. That's going to be something that's going to be important later on. Okay, then, so that's basically the code that you generate when you see a return statement. Then you eventually, if there's other statements, you would generate the code for other statements. And the last thing that you should do before you get out, basically before stat block finishes here, and comes back to here, it should actually generate JRR15. So that when you execute this function, even though you did not encounter any return statement, it basically jumps back to the calling function. Okay. So that's to make it so that even though there might not be a return statement, you would still jump back. Okay, so that's it for a function definition using the tags-based mode of execution for function calls. Okay, so that's basically things that I've explained as I went in explaining the example. Fn is the alias you branch upon when you execute this function. Fnres is where you store the resulting value of this function, the return value of this function. You need to reserve a local variable for each of the parameters that you pass the values into this function. And then you use R15 to actually store the branching address, the address where you branched from, so that when you branch back to this address. Okay, so that's very important to understand that if you proceed in this way, for example, if you call this function with parameters, let's say 1, 2, okay? You call fn of 1, 2. And eventually fn is calling another function, and it was calling another function, which another function is that fn of 3, 4. And if this happens, then 3 and 4 are going to be passed into fn here. It's going to basically erase the 1 and 2 that was already there. So that this previous execution of the function fn is basically lost. Okay. So if you use this way, there can be only one call to fn that is active at any point in time. Okay. But for example, that would disallow that you have a recursive fn function. So this actually works, but it doesn't work if you start having more than one call to a function that is active at any point in time. Very important to understand this limitation. So again, if you do it this way, that's fine. If you're going to receive the marks for function calls, if you proceed this way, there's going to be another marking element for recursive function calls. And if you saw in the grading scheme for assignment number 4, there's no marking element for recursive function calls. So it means you could actually have the full marks for assignment number 4, even though you don't implement stack frames. Okay, so here is an example about how do you call the function. So this example was about how do you generate the code for the body of the function, or the function definition. Here, this is an example of how you would actually call this function. Here, I have an expression and, of course, another function. I have an expression that's making a call to this function fn and is passing some parameters to it. So assuming that this code here is in a function body somewhere, okay, so here's the tree that corresponds to this assignment statement here. So that's my assignment statement, assuming that it is in a statement block that precedes this assignment statement and with a statement, and that following this assignment statement, there's other statements, okay, which is not part of the example. I just wanted to show that this assignment statement is actually part of the statement block. Okay, so how does it go to generate the code for an assignment statement? So basically, you start by calling visit of the, or accept of the assignment statement. First thing it does, you see that it doesn't do anything itself before it calls accept. So you call accept of this one, it does nothing. It just calls, it delegates the acceptance to its children. So it calls accept here, calls accept here. And then when this add up actually, which is this one here, is telling its left operand to actually accept, eventually this sub-expression is going to proceed and eventually generate some code, which is going to be the code that you have here. Okay. So the first code you're going to have is the generation of the code for this here. Okay, so here, and then you're gonna actually have generation of the code for the left operand of the times. And then the right operand of the times is here. But you see that the left operand of the times is actually my function call. So my function call here is what I have in this white rectangle, which is the important thing that we are focusing for this moment. So how do I make my function call? So I must have some kind of branching, and before I do the branching, I must pass the parameters. And after I come back from the function, I must retrieve the return value. Okay. So my branching is actually happening here. So I jump to fn here. Before I jump, I actually have to pass the parameters. Now the thing is that these parameters can be expressions. So I need to evaluate the expressions, which, for example, might yield the evaluation of this expression here. We assume it is its entire tree and entire code, which would eventually yield something like PT1 as the result. So then I take PT1, and eventually I copy it into my memory cell for FNP1, which is the first parameter as we have defined before for my function. Okay. So here I basically computed the value of my first parameter and I pushed it into my label, my memory cell, which is label FNP1. So that now when you execute this function, it's gonna receive this value. And then you do the same for all the parameters. In this case, you compute the code for PE2, another mistake here, PE2, and then you put essentially the value of PE2 in FNP2. Then you do the branching, then this function executes, it knows it has been passed these parameters, it uses them, and then once it jumps back, then you take fnres, which is where you know this function has stored its resulting value. You put it into R1, and then you use it inside of this expression. So you see that the resulting value of this here is actually I should have 6 comma or colon 6 colon which one is it, T2. I should have 6 colon T2. So that this T2 is now the left operand of my multiplication operator. Okay. So 3 things. You need to jump. Before you jump, you need to pass the parameters. And after you jump back, you need to retrieve the resulting value. And then you use it as a value inside of an expression as any other value that is a result of evaluating sub-expression. So this is how you generate code for a function, by receiving parameters, being branched upon, and then generating the code, especially for the return statement, and then branching back. When you call the function, you need to have a JL to branch to the function. Before the JL, you pass the parameters, and after the JL, you retrieve the returning value. So last part is actually doing exactly the same thing, except that we're going to use a function called stack, which is how it is done in real life. As I explained, if you're using this static way of execution. It works, but it's not very interesting because you can have only one instance of a function that can execute at any given time. It's not very interesting. Okay, so basically here I'm going back and explaining why what we saw before, it works, but not very interesting. If you want to have things to work correctly while allowing more than one instance of a function to execute at any given time, then you need to have a, basically to allocate. The problem is the allocation of the variable, the values, memory allocation for the state of the function. What we done before is basically it was using static allocation. At compile time, it's decided where these values are going to be stored, which makes it so that there can be only one value for each of the local variables of a function. If you want to have more than one function instance to run at the same time, for example, if you want to have recursive functions, then you need to have a function called stack. Basically, the idea is that when you call a function, you allocate a block of memory for this function that can contain the values of all the local variables for this function execution. So that if you call this function again, then you allocate another block for this other instance of the function. Okay, so that preserves the state of all the instances of this function, and then you can have as many of these functions executing at any point in time. Okay, so basically, if you want to do that, then you need to have some kind of mechanism that will, allocate memory on the stack, and that you create stack frames, and so on and so forth. And as you're using stack frames, the idea also that comes with that is that you cannot refer to the variables by name anymore. You cannot refer as we used to do before. When you declared a variable of a certain name inside of a function, you had a tag that has the name of this variable, which was very convenient, which you cannot have, because then now when you have stack frames, you can have many of these variables that are, these local variables that are stored for as many function instances that you may have. So basically what we're going to do, we're going to use offsets. We're going to reserve a block for all the local variables of a function, and then we're going to use offsets to refer to these variables. But potentially, pretty much like we saw as I explained how to do offsets for the members of an object, for example. Another problem also, when you call, when I explained when you use JL, it uses R15. The idea is that if you use JL to call a function, and then you want this function to call another function, and you still use R15, then it would basically erase the value that was in R15 before. Then you're not going to be able to know where to branch back to the first one. Okay, so if you want to have more than one function that is called in a sequence, then you actually need to remember the value. Every time you call a function, you need to have not only store the return address into a register, you need to store it in memory. So that's also what we need to have if we want to have multiple functions to be executing at the same time. And what we'll do eventually is that we're going to store this return address into the stack frame. Okay, so here we have an example here. So we have this program function. It has these variables here. It's eventually calling this F1 function. This F1 function has local variables, and it's calling this F2 function. And this function, F2, actually has local variables itself. Okay. So eventually what's going to happen is that we are going to create stack frames for every of these functions. So how it works is basically you have the bottom of the stack, which is like the bottom line of your stack, which in our case we're basically going to use the maximal addressing value as the top of the stack. Okay, and then we're going to address backwards to actually address inside of this function called stack. So this f stack is essentially the absolute bottom of your stack. If you start executing one function, then all its local variables are going to be stored in what is called a stack frame. Stack frame is a block of memory that is allocated that will eventually contain all the values of all the variables that are declared inside of the scope of this function. So you see that when I start executing my program function, then my stack frame for my program function is created, which contains A and B. So A is an integer, so it uses only one memory cell, and then B is a float, so it uses 2 memory cells. Okay. The thing is that here I actually put that here as a reference. These are not tags. These are just basically to say what is contained in these memory cells. Okay, so if you're using stack frames, you stop having names anymore. Okay, the only thing you have is a block of memory, and then by knowing in what order these elements in your scope are being declared and what are the types, then you know, for example, the first word is for my A, and then the 2 second words is for my B. Okay. Again, don't assume that these have names as they used to have in the previous way I explained before. Okay. You just have a block, and then you're going to use offsets to figure out where to access each of your elements of this block, of the stack frame. So when I start executing my program, then first thing I have on top of my stack is my program function. These are not there yet. Okay. So as I start executing my program, I start having this stack frame on top of my stack. Then when I call F1, then this stack frame is created. Then when I call this function, what I'm going to eventually do is that I'm going to use a variable to actually store what is the bottom of the current stack frame. So when the program function starts executing, the bottom of the stack frame, of its own stack frame, is the bottom of the stack. But when I call F1, the bottom of the stack frame for F1 is bottom of the stack plus the size of the stack frame of the program function. Okay. So what I'll do is when I'll call a function, well, I'll always know what is the address of the bottom of the stack. So when you are about to call a function, then you create a counter that actually contains the current bottom of stack for the current stack frame. And then you're going to use this address plus an offset to refer to any of the elements that are in this stack frame. Okay, that's essentially, and then before you actually return from a function, then you will decrement this counter. For example, the program function starts executing. Before it actually calls this function F1 here, then this counter is increased to here. So that when this function executes here, whatever it is using as its own stack bottom is this address here, okay, which is bottom of stack plus the size of program. Then when this function executes, it refers to this plus an offset. Then when function F2 is called, then before the call is made, then this counter is increased by the size of the stack frame of F1, which is now this here. So that when F2 is executing, then when it's using its own offsets, it's using offsets relative to this address here. Okay. Then when function F2 ceases to execute, then the counter is actually decreased, so that now the bottom of the stack frame is this one here. The F1 can continue using its own addressing correctly. And when F1 ceases to exist, when it returns, then the counter is decreased to this here, so that program now is able to use its own addressing relative to its own stack frame. So the job here is to essentially create a certain counter. We'll actually use register 14 to store the value of the current bottom of the bottom of the current stack frame. Okay, and we're going to increase and decrease this R14. If we call a function, we're going to increase its value. If we are about to return from a function, we're going to retrieve. We're going to decrease this value. Okay. So here I've explained that, you know, a stack frame essentially is there to contain the state of a function, the values that are held by all the variables that are declared inside of the scope. So that's the bottom line idea of what should be contained in a stack frame. However, there are other things that need to be stored in the stack frame, as I hinted at before. For example, the jump address. So the jump address, normally, well, when you use JL and GR, you use R15. However, as I mentioned before, if you first call one function, then the return address, which is this one here, is stored in R15. However, if this function is calling another function and you still use R15, and this address here is forgotten. Okay, so what you do is actually, as you are about to, as the function starts being executed, it will actually store its return back, the address where it wants to return back after execution is going to be stored on the stack frame. So that's basically here, you actually will store, you will take this, as you come into this function, it's going to take the value in R15, is going to basically put it here in memory. And before it's going to use JL, it's going to retrieve the value from the stack frame here, and then going to put it into R15 and then call JL R15. Another thing that the function needs to store is its parameters. So just like when we said before, when you are about to call a function, you need to pass it its parameter values. So you need actually to have some memory cells that are created to actually contain these values, and these memory cells need to be in a place in the stack frame that is predictable by the calling function. For example, if the program function is to call F1, then from the perspective of the program function, before it's calling F1, it has to be able to predict when F1 is going to be executed, where in the stack frame it is going to expect that its values are going to be residing. Its parameter values are going to be residing. It's important to understand here that you're not allocating, you're not freeing, and you're not allocating a memory space. You're just basically playing around with the value of this counter here and saying now so when you are calling this function f here, f1, you basically increase this counter here. So whatever was here before is still going to be here. You're just basically telling this function, you may use this space as you want, okay? So it's not erasing the values as it returns, it's basically just moving this pointer up and down and letting the functions use whatever they want inside of this, starting at this address and then using offsets going up and starting at this address. So basically, when the program function executes, before F1 is ever using this here, it knows if it needs to know where the parameters of the function f1 are going to be expected to be by the execution of f1 before it calls f1. So for example, program function here is going to pass b and c to this f1 function. So it's basically going to compute b and c, and is going to actually be putting it here. Even though at this point in time, as the program function executes, this stack frame is not used by f1, okay? But it's the program function expects that when the f1 function is going to be called, that the f1 function is going to expect both of its parameters to be residing in these two memory cells. So basically, the program function knows that when it's going to call a function, then the parameters of a function are going to be at the maximal offset of its own stack frame, plus the size of a return value that of the function it's about to call, plus 4 bytes, which is the size of this, and then plus, for example, for parameter number 2 and parameter number 1 and number 2 are going to be stored inside of these memory cells here. It's going to basically be putting these values inside of these memory cells here. And because there's kind of a mutual understanding between all functions, this is how we'll proceed. And when the function f1 is going to execute, it's going to basically refer to these here as being my parameter 1 and 2. Okay. Okay, so basically that's what I'm explaining here. Okay. So that's how the parameters to a function are being passed. When a function executes, whatever is this function, for example, if a function f1 here would be to call another function, then it would expect, it would pass the parameters to this other function, which would be residing here. There would be the place here for the return value, then the jumping address, then parameter 1, then parameter 2. So function 1 here, if it ever would call another function, it would basically put the parameter values here in these memory cells. And then when the function, the other function executes, then it magically finds them at the right place, because that's the convention that we use for the code generation. Okay, so very important here, I'm going to repeat that later, that you see here that there starts to be a lot of different things that you have to do. So, and it's important to resist the temptation of trying to do everything. You know, I'm going to do all the code generation. And eventually, if you run out of time, then eventually it's possible that nothing is going to work. And you're not going to be able, you try to do everything, but you cannot demonstrate to the marker or me at the end that something is working. And then it's going to be very difficult to demonstrate your code generation if you cannot execute any program, any Moon program. Okay. It's very important that you come up with a plan of action. What is it that I'm going to achieve first? What kind of very small program can I compile and generate code for and demonstrate that it actually works, that the Moon code for this very simple program actually works? Then you start doing more and more and more and more. Okay, it's very important that you come up with a plan of incremental plan of action. Okay. So one of the things that you can do is to actually, as you saw in the code that I provided for the visitor, I had my the compute memory size visitor, which was actually computing what is the size of each of the variables in a scope, and then computing somehow here, which you would recognize as the offsets in a stack frame, for example, for a function. Okay. Another thing that you might have seen also from this, from these tables is, for example, you might see here that this program function has only 3 variables A, B, C. However, you see in the table there's T1, T2, T3, T4, and T2C to T7. What are these? Well, as we saw earlier, when you generate code for a large expression, you start having temporary results. These temporary results still need to be stored somewhere in the memory, okay? So essentially here, when I do this compute memory size visitor, it actually goes over the entire tree, and then it figures out that if it encounters expressions or sub-expressions, that it needs to actually create more temporary variables and actually puts these temporary variables inside of the memory of the symbol tables. So how do you make a difference between them? So basically all the vars are the variables that are declared. The temporary variables are a result of expressions being computed, larger expressions or sub-expressions being computed. And the literal values are, for example, if you say a is equal to 1, then this 1 still needs to be stored somewhere, which is, we might say, is a special kind of temporary result. So all this to say that, you know, there are things that you have to do in order to facilitate that you will eventually do your offsetting. For example, if you're using the stack frame method for a symbol for function calls, then you need to use offsets. Then you, by having a visitor like this that puts the offsets in the symbol tables, it actually solves a very large part of the problem of the code generation. Okay, another thing is that, well, you might see, for example, here I was talking about functions. Here you have the all the members of a function. That's basically all the members of a stack frame for this function. However, you have the same notion, but for a class. So that's basically this size here, and these offsets are representing the size of a stack frame, and then the offsets for each of the variables that are declared in the scope inside of the stack frame. But you also have the same notion for a class. If you remember, I explained before in the beginning of the lecture, I explained that you have to use, if you want to refer to the elements or the data elements of a class or an object, you must use offsets. So you can use exactly the same technique to figure out what is the size of an object and what is the offsets of each of the elements relative to the first memory cell allocated to the object. So having a visitor like this that makes these computations before you do the code generation is very, very handy. Of course, it needs to be done before you do the code generation, and this visitor would need to be triggered before your code generation visitor. So here's a full example showing, well, a full simple example showing how you generate code for function calls using stack, frame stack. Okay, so this is basically this program here. It contains 3 variables, A, B, C, assigns A to 1, B to 2, 1 to A, 2 to B, and 3 to C. And it implements this assignment statement here, which is composed of this expression here. The left operand of the times here is a function call. Then after I've computed that, then I output the value that's resulting from that. And when I call this function here, it receives these 3 parameters. It has one variable that is local to its own scope. Then it uses this expression to compute a certain value, which it puts inside of this variable here, and prints out this value, then returns this value. Now, if you execute this program here, it's going to basically execute this here, make these assignments, call the function f here, pass 1, 2, 3 into these here, and then it's going to output 7. And then we're going to make this computation here, and then A is going to take the value 17, which is going to output here. So basically, it outputs 7 and then 17. So you see here what's happening is that you have a function which is being called here, which is passed 3 parameters. which returns a certain value. And both of these are actually using a put statement or a write statement. Okay, so here's the code that is should be generated for a stack mode of operation for the program function. Here, I did not include a tree and so on because I tried to do it, but then I figured that it was actually making it more complicated than anything else. So I'm gonna try to be precise in my explanations here. If you have some questions, please don't hesitate to come to see me in online office hours. So here, basically what's happening is that you have these rectangles here. So you have one rectangle here, one small rectangle here. That's basically portions of code, okay? So you have my entry here and then my halt here. So that's basically the code that is generated as I am going the abstract syntax tree of my program function, okay? So get into the program function, entry, blah, 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 go over the tree and so on of these declarations here and these statements here and so on. And then at the end, I actually output halt, okay? Okay, so what does it do? So it, first thing that it does is generate codes for these three assignment statements, okay? As it uses stack frames, it does not generate code for res. As we saw before, when we were basically saying if you encounter int a, then you would go a res 4. In this mode of execution, we're using we're using dynamic allocation. So there's no such thing as res anymore. Basically assuming that this variable a is going to reside, oh, it's right here. The a, it's assuming that a is going to reside at the absolute bottom of my stack frame, okay? And that the, here is the actual offset I'm using to actually refer to A. So essentially, the address of my variable A is bottom of my stack frame plus offset 0. For example, my variable C is bottom of my stack frame plus offset -8, and so on and so forth. Okay, so you see that I don't have these res anymore. It's basically, all the variables are stored in my stack frame and I use offsets to refer to them. Now that's what these rectangles represent. So at one point in time, in the beginning, when I execute all of this here, there's only the program function that's being executed. So that's, in terms of my stack state, that's the only thing I have on my stack is my program function's stack frame. However, here, I will eventually be calling f. As you see that before calling f, you remember that when I explained before that I'm actually using R15 to increment a variable that is going to contain the value, the address of the bottom of the current function stack frame. Okay, so when I'm about to call f1 here, I actually increase this variable by the size of the stack frame of a program function. So that now when f1 executes, it's going to use this address as the base plus its own offsets to refer to its own variables values. So when I start, I only have the program function as a stack frame on the stack. Then here, I'm about to call f. So what I do before I call f is I actually increase the stack, the bottom of stack frame value, which is stored in R15. I increase it by the size of the program function. Where do I find this? Find this in my program function here. The size of the stack frame of the program function is 24. So I basically increase this variable, which I store in R14. I increase this variable by 24. Now, this R14 contains this address here, so that when F is executing and it's using its own offsets, then it's going to offset starting at the value stored in R14. That's how I end up having a stack frame stacked upon the previous stack frame. You see that I'm not allocating these memory cells, I'm not freeing them, I'm just basically having a pointer, points up, 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 down, 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 so on. That's all the only thing I'm doing, okay? If I do my math incorrectly, everything's going to break loose and then it's not going to work anymore. That's one of the things that is difficult to, if your code is not working, it's going to be difficult to figure out why it's not working. However, if you're using tags, then it's much less problematic to debug if it's actually your code, the generated code is not working. Okay, so here I had only the program function. Here I'm about to call this F function. Before I call F function, I increase my R14 by 24. Remember why I'm using minus? Because this address here is the maximum address in the Moon machine. So I assume this is the bottom of my stack. So if I want to go up on the stack, then I'm basically going down in numbers because my bottom of stack is the maximum value. That's why I increase, I go somehow up in the stack by decreasing the address. That's why I have minus values here. Okay, so I'm about to call F. I increase my R14 to this here, call F, so that when F is called, it's gonna offset starting here. It's gonna use these memory cells here. After F is returned, I'm gonna come back here. That's basically F does not exist anymore. So I can actually reset my counter to this here, which is gonna be basically this situation here. So I go back to the situation I was before I actually call this function. Note that the values that were used by F here are still here, okay? They're just been lost somehow. They are still there, but if you would call F again, then it would still find them there again, okay? That's actually how as much crude as it looks, as explained like this. You'd be surprised to see that when you use the C language, for example, that's exactly how it works. That's why it sometimes is difficult to figure out why. Sometimes functions are working and sometimes they are not working because they are using this mode of execution. If you're calling twice the same function in succession, it might continue to work because its values are still there on the stack. And it's using the values that were put there by the previous execution of this function. However, if you use another function in between these two function calls, it doesn't work anymore. Anyway, close parenthesis on this. So you might think this is very crude, but that's how a kind of a low-level language such as C or C++ is actually working. Of course, it's much more complicated than that, but the idea of it being crude is right and is also part of how C and C++ are working. Okay, so after I'm back here, then I'm actually executing the continuation of the evaluation of my expression here. That's basically my expression here is being, the code is being generated for this expression. Keep in mind that this, my left operand of this expression was this function call here. So that's why I had to make a function call in order to evaluate my left operand of my times operation. Then here I continue doing the evaluation of my expression. Then eventually I call my put or write statement. As I explained before, I'm not going to explain it again, but here it's basically passing parameters to int string and then calling put string. And then eventually the last thing it does before it goes out here is to decrease the stack frame counter so that it will eventually at the end here, the stack frame counter is going to be at the bottom here. Okay, note that here I'm actually showing that these int str and put str are actually using a stack frame. And that when I'm passing these parameters to int str and put str, I'm actually putting them here at address -8 and -12. For int str, I'm putting both of its parameters here. And when I'm calling put str, I'm putting its parameter in address number -8. Okay, so this is how the code is being generated for this program function here that's making a function call using a function call stack. Okay, so let's see what's happening when I'm calling this function f here. When I'm calling this function f here, I'm actually jumping to this other piece of code, which is the implementation of the function f. So the first thing that it's going to do is it's, well, as we saw before, when we were using the tags to actually receive the parameters, then it would actually have some tags to store these values. And this mode of execution, if you see when you call the function, before you call the function, you actually, as you are executing this here, before you make the call, you eventually take the values of A, B, and C. So I take the value of A. What is the value of A in my program function? A, B, and C are 0, 4, 8. So you see that I'm taking 0, 4, 8, which are A, B, and C, and putting them in -32, -36, and -40. So literally I'm taking 0, 4, 8, 0, 4, 8, which is my ABC, and I'm putting them into -32, -36, and -40, which happen to be where F1 or F is going to be expecting is P1, P2, P3 to be. So basically here I'm passing these values onto the stack frame, which does not exist at this point. But I'm putting these values here because I know, because I have this agreement with these other functions, this is where we all agree we pass our parameters. So when the program function calls this here, it knows it can predict where this function is going to expect to have their parameters when they start executing, so that they will be offsetting with regards to this baseline here and be able to retrieve their parameter values. So that's basically the parameter passing that's done here. So you see that there's nothing that is being done here to receive the parameters, because the last thing that the calling function did is to actually, what did I do here? Okay, the program function actually copied that here. So this function f knows that P1, P2, and P3 are in offset 8, 12, and 16. So you see that it's using 8, 12, and so on, and 16 as P1, P2, and P3. So, okay. So the first thing it does is actually implement code for this assignment statement here, including this expression. So this is the code for this expression here The last thing it does, it actually puts the result of this temporary value. The temporary value of this right-hand side here is minus 28, which is this one here, which is T2, okay? So literally minus 28 is T2. So that it's basically taking T2 and putting it into minus 20, which is my ret val, okay? So ret val is essentially, I'm putting T2, which is the result of this, into ret val, which is actually stored here at offset minus 20. So you see that, you know, this is much more cryptic. This code here is much more cryptic than the code that if you would be using, that you would have if you would be using labels. If you have labels and inside of your code, then you see the label name. So you somehow are able to trace this code and see if it's correct. However, if you're using offsets, then you need to have the table in order to, you know, see if you're doing the correct thing. If your offsets are correctly calculated, or if you refer to the right variables, then you need to be able to see from the table if it's using the right offsets. Okay, but that's one other reason why using semantic, not semantic records, but the stack frame execution mode, because it uses stack frames and because it uses offsets, which are more abstract, it's more difficult to actually figure out why it's not working, if it's not working. Then, as we may see, then we're using put or write, which is basically using a stack frame of its own, just like I explained before. Then last thing you have is return, so that you see that what it does, return ret val. So ret val we saw is offset minus 20. Ret val is offset minus 20. So it's going to basically take ret val, is going to put it into the memory cell that we have allocated for our return value, which is offset 0. So it's taking minus 20 and putting it into offset 0. R14 being the bottom of my current stack frame. Then, okay, there's the jump also. When you're about to jump, yes, okay. So when you, the first thing you do here, the first thing you do when you get into the function is to take the value of R15, which is the JLJR address, or the jump address, and you're putting it into this memory cell here, okay? So that when you're about to jump back, then you retrieve the value from the offset minus 4, you put it in R15, then you call JR R15. So this way you can store your return address inside of your stack frame. And thus you can call as many functions as you want without fearing that you're going to lose your return addresses. Okay, so that's about it for this quite elaborated example. I hope this was clear. Again, if you have some questions, absolutely don't hesitate to contact me either by email or by coming into one of my Zoom office hours. Now I'm going to say a little bit more about the strategy you should adopt for, you know, from this point forward in the project or for assignment number 4. As I hinted at before, there's a lot of different things to be done. Okay, and a lot of these things depend on other things. So there's clearly some kind of sequence that you should figure out if you want to eventually generate code for programs that you can execute. There's a certain order in which you should proceed. That's the order which I propose. First of all, you should process the variable declarations. So if you're using tags, then you need to know, when you use res, you need to know what's the size that you need to reserve for. If you're using offsets and a function called stack, then you need to know what is what are the offsets and what's the size of a stack frame for each of the functions. All this to say, you need to figure out what's the size of each of these blocks. So that's the first thing you should consider doing. Okay, before you generate any code, you should have the same visitor I have provided you with for the generation of the size of each scope and the offset inside of the scope for each of the things. If you want to do stack frame execution for function calls. Even if you don't use stack frame execution, you still need to have offsets for the objects. Okay. You need to have offsets also for arrays, but that's a different issue. If you want to have objects and you want to be able to refer to the elements in the object, you need to actually determine the offset of each of the different elements inside of an object. There's no way around it. If you want to have objects, you need to have offsets. So after you determine the size, then you can do the memory allocation. If you want to use res and the tags, then you can straight away start generating your res instructions. Then what you should do is to go and generate code for some expressions. As you saw, it's quite easy to figure out how to do the implementation of every of the operators. So you do one operator after the other, then you check if it works when you combine operators together. Then the thing is that you're not going to be able to observe whether the code is correct at this point in time. Well, at least if you execute the code and it doesn't crash, the Moon code, and it doesn't crash, it tells you, well, maybe it's correct. But you really know if it is correct when you're able to make it output something to the console, which is when you start having the implementation of the right statements, okay? So you should aim somehow to being able, along the way, very early, to have the right statement. So as soon as you have expression and right statement, then there's a whole bunch of things that you can do and see if it actually works. Another interesting thing that you need to have if you want to have interesting programs is the assignment statement. Basically, you should aim for these 4 different things here as one of your first goals. If you want to execute code that, if you want to generate code that executes and that you can verify that executes correctly. Then once you have this, then you can add conditional statements and loop statements. And once you have this, that basically would mean, because at this point in time, if you do all of this, the only thing you can have is a main function that can have some variables, possibly only integer variables, has some assignment statements with a long expression, and then prints out the value of this expression. No function, nothing. So the only thing you can have at this point in time is a program function, okay, with some statements in it, and that you can print the value. It's a very interesting. Normally when I have people at the end that can achieve that, they have a reasonable grade. Not saying they have a stellar grade, but that's a very reasonable subset. When I see that at the end, if I see that, I'm happy to see that. Okay, and then the more tricky parts, of course, as I just explained now, function calls. So as you saw, it's not like rocket science. It is a little bit complicated, but it's quite easy to do if you have some time to invest in that. And that's one of the things about the remainder of the project. It's about how you're going to manage your time. What is it that you're going to achieve in the time that you have? Okay. Some people have more capacity, can code faster than others, or have more capacity to understand things and get the things from the first time I explain them without having to struggle too much. So that's how basically I make a difference between somebody who's a stellar student versus some other people that might struggle a little bit more. Okay. So from now on, that's how I make a difference between who's excellent student and is able to do everything I asked for, versus other students which did not have time or struggled to implement some of the things that I asked for, versus other students which were just basically utterly confused at the end. Okay. Hopefully and regularly, I don't see that many students that come at the end being confused. Very important that when you come to the demonstration, the worst thing that can happen is you come to the demonstration and you see, I observe that it doesn't work. And I also observe that you don't know why it doesn't work. Okay. So that's the worst thing that you can do. So at least if you come at the end and it doesn't work, be prepared to explain to me why it doesn't work. Okay. And what would you need to do to actually make it work? Okay. If I observe at the end that you have most of the things that don't work and you're not able to explain to me why it doesn't work and what needs to be done to fix it, you're in trouble. Okay. But if you have things that don't work and I feel that you are in control of what's happening, then you're in a much better situation. Okay, tricky parts, of course, function calls, expression involving arrays or classes, anything that involves offsets, you add a little bit more complexity to the equation. Floating point numbers, I have to say that floating point numbers not very often I see some people doing that, so don't think this is a very high level requirement. You will see, I will very soon put out the grading scheme for the final project. You will see that this is actually very few marks. Implementation of a function call stack, as I just explained a few minutes ago, difficulty of it is that it's going to become, your code becomes very abstract. So if it doesn't execute anymore, it's harder to figure out why it doesn't work. Why is it that the Moon code does not execute correctly? Because it's using the stack and the offsets and so on, it's harder to figure out what is wrong with it. Anything involving objects requires offsets, especially if you have arrays of objects or an object that contains arrays, objects that contains arrays of objects, and you have several levels of offsets calculation that combine together. This is actually, of course, increasing much more on the complexity. But the point is that if you are able to have objects and you are able to have arrays, then it's just a little step to be able to have arrays of objects. Okay. But you see that it's basically stacking up on things that you need to first understand, figure out how to do it, and then have time to actually code it and then make it work. Another tricky part, which I don't see very often, is call to member functions. The member functions are, the only thing special about member functions is that they have to be able to refer to the members of their class. You see, when you have a function, my eraser. If you have a function like this function f here, so this function here has basically two things in its own scope, a and b. If it's a free function, that's the only variables that it can actually refer to. However, if this function is a member function that is member of a class, let's say class A, which declares a member X, then suddenly you start having the possibility that this function can actually refer, let's say B is equal to X. So this function, because it's a member of this class here, can refer to the elements of the class to which it belongs, okay? So that's basically the difficulty, one of the difficulties of, or the main difficulty of doing member functions. There's no difference in calling them or passing parameters, return value, everything is the same. The only difference is when you want to have a member function access the values of the state of the object to which they belong. A trick about this is to actually have pass by reference the address of the object, so that you can actually use the address of this object using offsets to actually refer to the members of the object itself. Okay, so calls to member functions. It's a little bit tricky simply because of that. It's not entirely different. It's just a little bit tricky because it can refer to the members of the object to which it belongs. So the final thing is, as I just said, you'll not fail the project if you don't have the implementation for many of the code generation. However, you might fail if like you come to demonstration at the end and like nothing is working. So every time you add something, as much as the complexity is increasing, if you add something more, it makes it more and more likely, as you may know, I'm sure you know as a programmer, more a program becomes complex, you add to it, you run a better chance that it's gonna fail if you don't have control, if you don't understand what's happening anymore because it's too complex, you run the chance that it's gonna totally not work anymore. So that's what you want to avoid at all costs, so that you try to do so much before in the last days before the demo, so that you basically lose control of your code, and then you come to the demo and you're like, it doesn't work anymore, I don't know why. So that's what you want to avoid at all costs, okay? So basically don't try to do too much. Try to stay in control about what's happening, and basically proceed by one small step at a time. So for those of you who know how to do regression testing or unit testing, that's a good way to actually avoid that. One of the reasons why you might lose control of your own code is that you proceed with many steps and then you don't realize, but in this step here, you actually broke something, but you were not able to realize that something was broken. So you continue adding upon this broken thing, and then several steps later you realize that you broke so many things that you didn't realize, but then you don't know where to go at this point, and maybe you have to go back and so on. So the thing is that if you can test every step of the way as you go forward, then you can have some feeling as to whether or not you broke things as you went forward. Okay, that's one of the reasons why unit testing is so good. It's a good practice to have. So make sure that when you review the grading scheme at the end for the final presentation, that you are able to properly demonstrate what is actually working. There's going to be basically a checklist. And basically in the project demonstration, I'm going to go over the checklist. I'm going to ask you to demonstrate each of the things that are on the checklist. So make sure that you're able to demonstrate each of these things. If you know that some of the things that are on the list are not working, then you can explain to me how you had in mind to actually solve these problems. If your explanations are clear, then I might give you partial marks. If some of the things are, for example, you may generate code, but you cannot execute the code. So you have to be ready to show me the code that you generate and explain to me somehow clearly why this is a correct code, even though you cannot execute it, okay? So even if your own code does not execute, if you're able to show me that it's the correct code, but it doesn't work because it doesn't have the entire thing together, so if you can demonstrate to me clearly that the code is correct locally, even though it doesn't execute, then I'll give you some of the marks. It's important that you be able to explain to me. If something is going wrong, I'm going to be expecting that you can explain to me why it doesn't work, or how would you fix it so that it works. So that's some references. As you may have seen, there's a documentation for the Moon machine. I invite you to read it. The lab instructor is referring much to it into his slides and his upcoming video. I saw what he's working on right now. It is very much complementary with what I'm providing. So both of these things work well together if you want to have more information. Okay. So that's about it for me today. So I'll see you later on a upcoming video. Thank you. Bye.